So what is linear momentum and impulse? So that's what we're going to be defining and then talking about. I'll give an example as well, and I'll try to explain it to you. So you can see here the formula for linear momentum. And linear momentum is nothing else but simply a vector quantity. So it is a vector, and it is dependent on, you'll notice here, on the velocity of the object. So it describes the actual motion of an object in a straight line. So hence the word linear. So now it will depend on both mass and velocity of the object, and basically just the multiplication of the two. However, as you know, mass is just simply a scalar, and velocity is a vector. So the multiplication that we have in here is that you have a scalar multiplying or scaling the actual velocity of the object. And that particular direction of that velocity that you have is going to be exactly the same direction that the momentum is going to take on. Now, normally when you're studying this, and this is kind of the beginning, grade 12, when you're studying momentum, it is going to be linear momentum. So it's basically in a straight line. Of course, they can change. There are other momentums, and I'll mention that in a moment. So if you're talking about linear momentum in general, so here is the unit, and that of course shouldn't surprise you. Why? Well, because of the fact that you know that mass is in kilograms, and also your velocity is going to be in meters per second. So hence that would be the actual unit that you have, and you're seeing this, okay, right here, and then outlined right there. So that's what linear momentum is. It's pretty interesting because it just gives us a gauge, okay, of the amount of size that you have that an object carries a mass, and then it is moving at a certain speed. And obviously the more mass that you have, the more momentum you're going to exhibit. And you can think about that. If you have a big truck which is rolling along, it doesn't actually have to go pretty fast, yet it will have a lot of momentum. It will be very difficult to try to stop that particular truck. So that's what momentum is going to be for us in this particular chapter. So now here's an example that I would want to be able to show you. So it's not very difficult to try to gauge and then calculate momentum in general, especially in the beginning stages. So here is one example. So here's a given. So we have a car. Its mass, I'm going to put a little C here for the car, is 1800. So, you know, it's relatively big, although it's not a huge car. So there's definitely cars that weigh much more than that. Its speed, as you can see here, is equal to 25 meters per second. Now, notice that the actual value here is speed, so they're not giving us direction, and that's fine. You can still calculate momentum even if you don't have a direction, but be mindful that momentum is actual directional. So when you're calculating this value, if we're going to be calculating this and multiplying these things together, and then that particular momentum is going to be just the magnitude of the momentum, and of course we don't have enough information here to obtain the direction of that momentum. So here now, if you're going to be comparing this, you know, car to a small object, so notice something like a bullet, so that's going to be M of, I'm going to put little b in here, so it's very, very tiny. Notice that everything has two significant figures in here as you're going in. It is moving at, so maybe I'll put C here and a little b here. So it is moving at, so this bullet is pretty quick, right? So 890, so almost 90 meters per second. That's super fast. But let's compare these two results when it comes to actual momentum. So it says, you know, compare the two. So we'll do that. So if you have a car and you have your bullet and you want to be able to calculate these two, so that's not difficult. Again, I'm going to drop the vector notation because of the fact that we're not dealing, okay, with the actual vector. So this is going to be of the car, and then on the other side we're going to have the same thing, except this is going to be of the bullet. So put a little subscript B. Now if you substitute these in, so this is going to be 1800 multiplied by 25. On the other side, you're going to have 0.08 multiplied by 890, and both of these, of course, are going to give us our values. So let's just calculate that. So there we have it. Okay, so as you're looking at this, notice one is basically around 7, and then the other one is, 45,000, okay, which is enormously big. Okay, so for this particular example, so that's what we have in here. So in terms of a comparison, so clearly, this is way, way bigger, okay, than this, although the bullet is, speeding along pretty quickly. So that's an introduction. Okay, so now you have a definition, okay, for momentum. You have the actual formula for momentum, and now you've seen an example. Now this example is not very difficult, and that typically is something that you would be starting off with, although in future videos, you might see a little bit tougher examples. Okay, so now with this, I do want to give you a little bit of a note. Okay, so here is a note which I prepared beforehand. Now, linear momentum is not the only kind. So there is angular momentum. However, when you're studying this in kind of grade 12 physics, as you're beginning it in, or maybe in grade 11 physics, depending where you have it, okay, or somewhere else, normally you're not going to be talking about angular momentum per se. Angular momentum obviously has to do something with angles and rotations. Okay, so this actually describes the rotational components, okay, or rotational motion. In here, we're defining just linear, so in a straight line. So now rotational would not be talking about masses, but it would be talking about inertia, and it would also be talking about the angular velocity and not the linear velocities in straight lines. And this normally, if you're going to continue on into physics, maybe engineering or some other courses, you would be running into this inertia and angular velocity, and therefore angular momentum, okay, most likely in post-secondary settings. All right, so just a note for those who are studying this concept. Now, going from linear momentum, what we can now do is we can start talking about impulse. So what's the difference, okay, so here between impulse and linear momentum, which I'll just start saying as momentum in general. So impulse is the effect of a force which is applied over a time interval, and it causes a change in an object's momentum. So if you do have an external force that is carried out and it is applied over a certain amount of time, okay, then it causes a change in momentum. So here, in terms of its definition, again, it's not very difficult. It is a vector, so impulse is a vector. We normally don't write it as capital I. Capital I is actually typically for inertia, okay, in general. So we are using capital J. So you'll notice here that you have the vector notation, and this would be the force. This is the external force that would be applied over, okay, a certain amount of time. So the two are multiplied together. And this can, of course, be also written out as simply as the change in momentum. So impulse is the change in momentum. And now don't forget that change, this means that whatever that we have in here, so this would have been the momentum final minus the momentum initial, or 2 minus 1, that would have been the actual change. And now within here, so this means that this is mass times the velocity final that you have minus mass times the velocity, okay, initial. So this is the actual change. And this value, once you calculate it, is known as impulse. So with respect to impulse in terms of its units, so I'm writing out here the units. It's either in, so notice because forces are in newtons, and obviously your change in time would be in seconds, at least in the SI system. And if you're going to be defining it over here, of course, as the change in momentum, and you'll see, I'm going to just derive it in a moment, why these two are equivalent to each other. So this, of course, the change in momentum is simply nothing else but, well, kilograms meters per second. So these two can be used for the unit for impulse, and they're used often interchangeably. And the reason for these is relatively simple. And of course, the change I have defined over here. Now, why is this equation this way? Now, of course, depending on what information is given to us, then we can do the calculation either with forces and time, or I either with just simply if we know the initial momentum and final momentum, or possibly if we know what the initial speed and final speeds are, and then the mass of the object. So this equation comes from here. So if you recall Newton's second law, so Newton's second law said that the net force, I'll just write F, okay, for the net force, is equal to the mass over, okay, the acceleration that you have. Now, of course, this definition, okay, so mass times acceleration is just simply mass times the change in velocity, okay, all over, okay, the change in time. That's by that definition of acceleration. So if we know that, well, here we can now rearrange this. So we can take the delta t at the bottom and we can shift it over. So when we multiply this right here, so we bring that over on the other side, then the mass and the delta v remains on the right-hand side, and there you have it. Okay, so here is your impulse. So that is our impulse by definition. And then this right here is, of course, the change in momentum. Okay, so that change in momentum comes from the fact, okay, that we have this change in velocity. So that returns back, so you can use this or the forces and the changes in time. So that's impulse. Now, here's an example, okay, so a little bit of an example within here, and let's try to calculate, okay, this example. So here we have a baseball, okay, so we have the mass of the baseball, okay, so 0.15 kilograms. It is hit by a bat, and notice that its velocity, so basically changes. So notice that V initial, okay, is equal to -30. This is meters per second. So we would be assuming, of course, this is relative to some coordinate system, so either horizontal, vertical, it does not matter. But notice that they defined it negative and positive. So just with respect to a reference, as we are kind of used to the coordinate system, let's say in this case, you know, this would be in the positive direction, and then in the opposite direction would be negative. All right, so we have this, okay, as our initial. So with respect to the positive, it's traveling in the opposite way. And of course, for a baseball, well, it comes in, okay, into the batter, and then it's hit, so it goes over in the opposite direction. So that would have been my V final, okay, within here, these two, that is now 50 meters per second, okay, so this is what I have there. And now I can calculate, okay, the full out, okay, so within here, I guess I also have a change in time. Okay, I can calculate what the impulse is, okay, and what was it delivered, and then also it says calculate the average force for that applied, okay, hit, okay, in terms of the baseball. So here, the delta t that I have is 0.010. I guess I'm going to need that in a moment. So here, in terms of the impulse that I have, I guess I can drop, I'm going to drop the vector notation as well. Okay, so here, since I am given the mass and the changes, so I'm going to actually do the delta P, and that would have been M and multiplied by V final minus V initial. Okay, so this right here is your delta V. So that's just from the equation up above there, as you see there. I'm going to substitute. So that's my impulse. All right, so there you go. So we've calculated that one. And now if you want to know what the average force is, well, we know that J is equal to the, okay, force, okay, so the total amount of force over delta T. So since I have this, so this is 12, I also have this. So the only thing that's missing is that F, which now I can calculate. So this is going to be relatively simple for us. So F, 12 divided by, and 0.010. Okay, and there you have it. All right, so that means, okay, this is going to be 12, okay, 0 newtons. Okay, you can double check that on your calculators if you wish. So now we have an idea with respect to impulse. Now, please note and keep in mind that when you are doing these calculations, these velocities, they don't have to be collinear. So meaning, they're not going to be necessarily just in one or the other direction. They can be at an angle, right? So for instance, you can have one going like this and then one going like that. And then this would have been a vector in terms of subtractions, okay? If you do start having angles in, let's say, 2 dimensions. So then you would have to break it down, into its components and then use sines and cosines to break it down and then do the regular vector, in this case, subtraction between the two to obtain what your impulse would be. And in those situations, you can also obtain what the angle would be, right? So you can start to get your directions overall. So in this case, okay, so as we have this is in the positive direction overall, just because this was all nicely in collinear. So that's pretty simple, but you can certainly use it, okay, with angles as well. Now, the last component that I'll mention in this introduction, okay, is this concept of force time graphs and how they're relating towards impulse. So because impulse is nothing else but simply the force multiplied by the change in time, so if you're doing that multiplication, if you're lucky enough, and sometimes you are given the force time graph, so for instance, if you have something like this, so let's say that you're graphing things out, and someone tells you what the force is, okay, and then how it's changing in here, okay, with respect to time, then because of the fact that impulse is defined by the multiplication of the two, so within this case, you will know that the impulse is actually going to be the area under the curve. That's what it will have. And in terms of the calculations for geometry, especially as you're beginning this, you're most likely are going to run into, okay, either rectangles or triangles, right? So if you're calculating areas of these, that's not very difficult, right? We all remember rectangles and triangles in terms of the area. Now you can also calculate it once you get into calculus, okay? You can recall that this would have been integration. Now, for those students who haven't heard of that as of yet, because that probably means you haven't gotten into calculus, or at least not into calculus full out, then you don't have to worry about this. But in terms of the area under the curve, okay, doing rectangles, triangles, okay, trapezoids, etc. So knowing those is kind of important. So here, if you wanted to calculate what the impulse is, so imagine, I would come along here, okay, and then I would tell you that the force for a certain duration, all right, so let's say this is right here, and let's say this was 5 seconds, and then the force, let's say, was 10 newtons right here. So what this is saying is, if you want to know what the impulse is, all you need is to know what the area under the curve is, because you're just multiplying the two. Right? So here, in terms of a rectangle, well, the area under the curve is your impulse. So that is your area. And again, so notice that's force times your change in time, okay, overall. And of course, this would have been just 10 multiplied by 5, or 50, as we would have it, okay, Newton seconds. And that would have been your impulse overall. If it turns out that you have, triangles or anything else, okay, for that matter, so let's say if I would change this up, and instead, I would say, oh, we have something like this, okay, so obviously the area under the curve is not going to be just force times your delta t in this case. So here we would have had a triangle, so that would have been 1/2 times your base and your height. So in this case, it would have been 10 multiplied by 5, and of course that would have been 25 Newton seconds, and that would have been the impulse. And you can now combine, right, rectangles, triangles, or anything else, okay, that you would have. All right. Okay, so that gives you a sense and an introduction, okay, to these force time graphs and impulses if you do run into them. And now, just to summarize in here, I will include actually this full out nice document, okay, so which summarizes what I've talked about, in here. You can download it from the description or the show notes. And here is the summary. Okay, so linear momentum again, so it is just simply the, by definition, that would be the mass, and then the linear velocity of the object, okay, and you are multiplying the two. Keep in mind that it is a vector. Impulse, on the other hand, is the change in momentum. All right, so we have momentum right here, and this is the change in momentum that is known as the impulse, or simply what is the force that is exerted multiplied by the change in time. Okay, if you are given force time graphs, then the area under the curve gives us the impulse overall. Okay, and then, you know, you should note that, of course, understanding these has to do something with collisions, okay, protective gear, etc. Okay, so you're going to be running into these collisions, and you'll do that in future videos. All right, so that's it for this introduction. Thanks for watching. We'll see you in a future video. Bye, everybody.